Okay, chain rule. Chain rule is another rule we use to help us find derivatives of functions that are like basically a composition of two or more functions. Okay? What I mean by that, maybe I'll kind of start with an example of this. Okay? So let's say I have some function and it is, I'll go 2x cubed plus 5x raised to the fourth power. Okay. And I asked you to find the derivative of that function. Okay. Because you have a function, a quantity, being raised to a fourth power, if you really wanted to, you could take this times itself 4 times, get that simplified answer, and then just do the simple power rule on all of those terms. You'd get the right answer. But it would take a lot of time. I mean, well, yeah, if it's negative, well, yeah, then you could make it into a quotient eventually, and then use the quotient rule. But you're going to like the chain rule so much better. Okay? This is really two functions put together. Alright? You have, so my h of x, in this case, is what's inside my parentheses. So my h of x is going to be 2x cubed plus 5x. And my g of x is really just x to the 4th. Because if you think about it, if I take the h function and plug it into the g function, so in other words, I'd be taking this and substituting it in place of this x right here, wouldn't that put me right up here?
So it'd be okay.
If I take h and substitute it into g, so if I take 2x cubed plus 5x and just substitute it in for this x right here, that would give me what I have. You agree? Okay? So now, using the chain rule, okay, what I'm going to have, f prime of x will equal g prime. Well, how are you going to do g prime? 4x to the third, okay? But instead of writing 4x to the third, I'm going to write 2x to the third plus 5x to the third.
Oh, wait. Oh, yeah. Okay.
But then I just need to take that times the derivative of h. 6x squared plus 5. And there's a chain.
That's it?
We're going to simplify it, but you're basically done. That's your chain rule. An example of the chain rule. So, what you really did, okay, was you still kind of used the power rule. So you brought your 4 out to the front, then you had this raised to the third power. But because this is more than just x, you have to multiply that by the derivative of what's inside. You're actually kind of using the chain rule even when you did the derivative of this early on. When you did the derivative of x squared, you were really using the chain rule.
We just didn't know it.
Because that'd be like 2 x to the first times, what's the derivative of x? 1.
So why do we even use the other ones when we just always teach it as the chain?
Well, you certainly could teach it, I suppose, as the chain rule right away.
And then you wouldn't have to know
It kind of makes me angry.
Well, kind of you do. Because you got to know how the power, because without the power rule, you couldn't do the first part.
then you still have to know like the product and
Yeah. Yeah, you can't get away from Real quick, I'm not gonna do this, guys. Pay close attention. I'm not gonna raise this to the third power, okay? That's gonna just remain in my answer. So I'm gonna have 2x to the third plus 5x, and that's all raised to the third power. Now, is this a pretty easy multiplication, 4 times that?
Yeah.
Sure. 24x squared plus 20, right?
Yeah.
That's probably good enough.
Probably or is.
That is.
Okay.
Yeah.
You can use that one rule and
That's probably good enough.
Good.
Like
That
see
seems
that?
like a
Yeah,
waste.
that's.
Jake.
Oh, that's fine.
Okay.
Can you kind of just think of it as like moving the 4 to the front and then like it's the same thing as x squared, where it's like you just move the exponent forward and minus it by 1.
But then just remember to multiply by the derivative of what's inside the parentheses.
Yeah, but like, I'm saying, can you do that as like a shortcut kind of? If you can still think of it right.
Yeah. Yes.
Could you do now the square root of 2 over, was it 3 minus, 3x plus 1?
What now?
The one we just did before, or?
Yes, then when we have a negative 1 power, we could use this change. And I'll do one with a negative here eventually. But, okay? Now, that's one way to do it. Okay? That's one way to do it. This is where you have to try and rewrite the function that's given to you as a composition of 2 functions, or thinking of it as a composition of 2 functions. Okay? The process is not overly difficult, but I just wanted to show it to you that way. What this business is saying down here is what's called kind of using U substitution. Okay? I'll show you what that would then look like. Alright? By the way, this notation, this dy dx, that's like saying y prime equals, okay? That's just another notation for the first derivative. Okay, dy dx is the derivative of y with respect to x. We did the derivative of y with respect to x. So in other words, this notation, like if I had y equals 2x to the 5th minus 7, I could write dy dx equals 10x to the 4th. Or I could write y prime equals 10x to the 4th. I just want to make sure you understand this notation. It's just another notation for the first derivative.
Why does it, like, why with respect to x?
Because in a little bit, when we start doing implicit differentiation, you need to state which variable you're differentiating with respect to. In other words, which variable you're differentiating when we have more than one variable in an equation. So dy dx means I'm going to do the derivative with respect to the x variable. Now, all we've had is x for a variable so far, so of course we've been doing that. But eventually when we start getting into some physics problems, or where y and x are kind of mixed together in equations, we got to have ways to do the derivatives of those, and it's called implicit differentiation, and you'll definitely need to know which variable you're differentiating with respect to each time you do a derivative. Okay? So this just means the derivative, okay? Now I'm going to show you how this U substitution would work. So here's my original function. F of x equals 2x to the 3rd plus 5x to the 4th. Okay? So what I'm going to do is I'm going to, over here to the side, I'm going to let U equal 2x cubed plus 5x. I'm going to let U equal what's inside the parentheses. Okay? So now, really, what I have is, I'm going to write it y equals, okay, no, don't I really just have y equals U to the 4th power? Yeah. Because if I take U, this, and I raise it to the 4th power, that's what I started with, right?
Yep.
Okay. So let's do the derivative of this. Alright? So I'm going to write dy dx. I could write y prime, but I'm just so you can understand how it relates to this. I'm going to write dy dx. So now, what's the derivative of this? What's the derivative of this with respect to u? So in other words, what's the derivative of u to the 4th? 4 to u to the 3rd.
Oh, which is really right as one.
Mm-hmm. But then now we do need still to take that times the derivative of u with respect to x. So we still need to do this part.
Just do that.
Well, if u is this, what's du dx going to equal? What's the derivative of u with respect to x? 6x squared plus 5, right? So now I just plug back in what these u's and du's actually are. So my final answer will be 4. What do I plug back in place of the u? 2x to the third plus 5x times, what's du dx? 6x squared plus 5. It's called u substitution, so you can kind of rewrite the equation in a simpler method, do the derivative of that simple method, but just don't forget to take it times du dx at the end. Some people really like the u substitution. I don't see it very well. However, I will say this. Second semester when we go backwards, when we do what are called integrals, which is the antiderivative, it's going backwards from the derivative. I do use u substitution when I need to go backwards on a chain rule. I like u substitution personally when I'm going backwards. But I don't really use u substitution, me personally, but some people love this. Okay? So any questions on that?
I don't.
I'll do another one here. Okay? I'll do a negative exponent. I'm just picking g because to change it up. G was getting lonesome. Let's go 3 over x squared plus 1 to the 5th. Now, we could use the quotient rule, but within the quotient rule, I would have to use the chain rule. Okay? So instead, I'm actually going to rewrite this. 3 times x squared plus 1 to the what power? Negative 5. So now if I were doing this derivative, I'm essentially using my power rule. So I take the negative 5 times what's in front, so negative 15. And then x squared plus 1 now is going to be raised to what power? Negative 6. But then don't forget to multiply by the derivative of what's inside. 2x. So I'd have my final answer would be negative 30x over x squared plus 1 to the 6th. A lot better than using the quotient rule or the chain rule within a quotient rule. Questions on that? Nick? I will, but I'm going to shut this off just because I'm time purposes.